Hello everyone, I am Dr. Osman reporting once again from the University of KwaZulu-Natal, the premier university of African scholarship. In our previous lectures, we looked at material balancing using species balances as well as element balances, and in all cases we needed to draw up a degree of freedom table in order to establish some kind of direction and to even determine whether the process is solvable or not. And we've also noted that if the process degree of freedom is 0, then it means that the process is indeed solvable. Okay, and today we will test that theory to its limit by looking at implicit and iterative material balancing. Okay, previously you've looked at processes where the process degree of freedom was 0 and also at least one of the individual units or the overall balance had a degree of freedom of 0. However, what if the process degree of freedom is 0 but none of the unit degree of freedoms are 0? Okay, and this is essentially what we will address today. Okay, so let's get straight to it.
So let's look at the following example. Okay, so we have an ammonia plant and we have a feed gas coming in and we are given the composition, and it is catalytically reacted in a reactor to produce ammonia. Okay, so we just have a single reaction occurring and the products of this reaction are sent to a separator, which is in actuality a refrigeration unit, and this refrigeration unit separates most of our ammonia. Okay, so it separates 75% of the NH3 product per pass. So we have 75% of N3 of NH3 coming out in stream 4, and now the remaining process stream is recycled back to the reactor. However, in order to stabilize the buildup of inerts, and the inerts are CH4 as well as our component A in the process, part of this recycled gas needs to be purged. Okay, so we have a recycle and we have a purge for part of the recycle. Okay, so only a portion is actually being recycled back. And the purge rate is adjusted so that the combined reactor feed contains 18% CH4. Okay, so that's 18% there, and so that we have a conversion of 65% of nitrogen per pass. And the question is that we need to find out what each of the flow rates and compositions are for each of these streams. Now let's look at a degree of freedom analysis for this particular process. Okay, so let's consider our mixer, and we're looking at just species balances here, not element balance. So back to basics. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and from this we can determine that we have more components in stream 7, so that's 9, 10, 11, 12, 13, 14 for our mixer. For our reactor, we will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 stream variables plus 1 reaction rate, so that's 10 plus 1. Okay, so we have our 14 and then 10 plus 1. For our separator, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so that's 11 there for our separator. For our splitter, we have 5 components here. That will mean 5 here, so that's 10, and another 5, that's 15. And we can count for our total process, and it should add up to around 31. If we count our overall, we have 4, 5, 6, 7, 8, 9, 10 plus the 1 reaction. Okay, so that's 10 plus 1 there. In terms of our balances, we have a maximum of 5 components. So we're doing species balances here, so we're counting the number of different species. 5 for the reactor as well as the separator and the splitter. And that will give us a total balance of 20 for the entire process. And of course 5 for our overall balance. In terms of our specifications, we are given a flow of 1000 moles per hour to the mixer, so that's relevant there. And we are given 4 independent compositions, so that's 1, 2, 3, and the 4th one. There's it there. No subsidiary relations relevant to our mixer, so we have a degree of freedom of 4. So let's look at our reactor. We have simply one specified composition, no flow, and we are given a conversion. So our degree of freedom is 11 minus 5 minus 1 minus 1. Okay, so that is a degree of freedom of 4. Let's look at our separator. We only have the NH3 recovery as a subsidiary relation, so we can count that. And that will bring our degree of freedom to 5. Finally, we can look at our splitter. We have only the splitter restrictions. Remember, n is equal to 2 and s is equal to 5. So 2 minus 1 multiplied by 5 minus 1. That will give us a splitter restriction of 4. So now we have a degree of freedom of 15 minus 9, and that will give us 6. Now let's look at our process. We have to count all of our flows. So we are given in the entire process 1 flow, 4 independent compositions, our conversion, our recovery, as well as splitter restrictions. So that's 20, 25, 30, 31. So that will bring our process degree of freedom to 0. If we look at our overall, we have 1 specified flow and 3 compositions, and that will bring our degree of freedom to 2. Now let's look at this table for a second here. Okay, so we have our process degree of freedom being 0, and this ultimately means that our process is definitely solvable. Okay, this is the defining criteria. We must have our process degree of freedom to be 0 for the entire process to be solvable. However, where do we start? Okay, so we have very high degrees of freedom for all of our individual units, and we have a degree of freedom of 2 for the overall. We do have a flow, and the previous trick that we learned is that we can relocate our flow, we can relocate our basis. However, even if I move my flow rate and put a basis somewhere else, I'm still not going to get any of my degree of freedoms to be 0. So despite whatever trick we might want to try, we won't be able to get our degree of freedoms to be 0 for any of our individual units or for the overall. However, let's try and solve this problem. Okay, so even though none of the degrees of freedom are 0, we could start at the unit that has the lowest degree of freedom, and in this case the overall balance has a degree of freedom of 2. So we can attempt to write out our balances starting with the overall balance. Okay, and in this example Now these types of problems will ultimately involve carrying unknowns throughout the system until they can be solved either iteratively or implicitly. Now in this case we are starting with balances which have a degree of freedom of 2. Our overall balance has a degree of freedom of 2. So we can expect to be able to express all of our components in terms of 2 unknowns. Okay, so we need to carry a minimum of 2 unknowns, and we have this understanding already that if we try and solve this overall balance, we won't be able to get all of our components, but we can at least express them in terms of 2 unknowns because our degree of freedom is 2. Now, as you could see, for previous cases, for our other units, we have very high degrees of freedom. So as we move along from our overall balance, we can expect to carry even more unknowns. Now the idea is that we can write out and start our overall balance and express our variables in terms of our 2 unknowns. And ultimately, once we move on from our overall balance and go to our unit balances, our splitter, our mixer, our reactor, we will keep carrying over these unknowns until we can solve them at an alternative location, right, at an alternative balance. Okay, so let's look at our overall balances. For our component A, we have coming in at our feed that this is our input, and remember A is an inert, so it doesn't participate in this reaction, so it's simply input is equal to output. We have an input of 3, so my N6 of A, NA in stream 6 will be 3, so that's easily found. CH4 is also an inert, so the input is equal to output, and we can easily obtain our methane in stream 6 to be 12. Now let's look at our nitrogen. Our nitrogen participates in this reaction here, so we have an output of nitrogen which is N6 of N2, and that is equal to our input over here minus 1R. Okay, so that's our expression. And then for our hydrogen we get the same, so output is equal to our input negative 3R. Okay, so that's it over there. And finally, for ammonia or NH3, we have our output in stream 4 as well as stream 6. Okay, so N6 of NH3 plus N4 of NH3. I apologize for my bad writing. And that is equal to our input, which is 0. And it's being produced with a stoichiometry of 2, so that's plus 2 of R. Okay, or simplifying, we have N6 of NH3 being equal to 2R minus N4 of NH3. Okay, so as expected, we have expressed all of our components in terms of 2 unknowns, namely R and N4 of NH3. So these are the unknowns that we can carry over to our next balances. Now, with all components of stream 6 being known in terms of R and N4NH3, of course, we can now look at expressing stream 7 and stream 5 in terms of these unknowns, and hence solve our splitter. Okay, and note that even though we have solved for some of our unknowns here, it's still not enough to actually reduce our splitter degree of freedom from 6 all the way down to 0. So we will just have to keep carrying over our unknowns. Okay, and also note that we have a degree of freedom of 6 for our splitter, and solving for these unknowns, we have 5 unknowns here, which is now solved in terms of R and N for NH3. So now ultimately we've only solved for 5 things, so we have a degree of freedom of 1 at our splitter now. So we can expect to actually pick up an extra unknown when trying to solve our splitter. So now let's look at our splitter. And for convenience, I can define an X ratio where X is equal to N7 over N6. Okay, since the total flow equation will ultimately be equal to N5, which is equal to N6 plus N7. And now to obtain my stream 7 component flows, I can simply multiply by stream 6. I can multiply all the stream 6 component flows by X. So therefore I can express all of my components in terms of this new value X, where X is equal to N7 divided by N6. Okay, so let's look at component A, for example. Okay, remember that for component A, we figured out that N6 of A is equal to 3. So now we can simply express N7 of A in terms of N6 of A. Okay, so this is actually the same as writing N6 of A multiplied by N7 over N6. And this N6 of A over N6 is simply my mole fraction. Okay, so just take a while to actually interpret this, and this is the actual wisdom of using this convenient X value rather than having to keep carry over this entire cumbersome ratio of N7 over N6. There are of course alternative ways. We can define any other unknown and make our calculation convenient accordingly. Okay, now in the same way that we have expressed component A in terms of X for stream 7, we can also express our other components. Let's look at, for example, component H2, our hydrogen. In reality, my hydrogen is actually equal to okay, so remember that we have N6 of hydrogen, and this is equal to N6 of hydrogen as we've solved from our overall balance, and we are multiplying that by N7 over N6. And remember that N6 of hydrogen over N6 is my composition, and because we are looking at a splitter, N6 of hydrogen divided by N6 is also equal to N7 of hydrogen divided by N7. So this particular ratio here, N6 of H2 over N6, is equivalent throughout because this is a splitter. Okay, and we can apply the same for NH3. We've proved that N6 of NH3 is equal to 2R minus N4 of NH3, and we are multiplying that by X, so that's simply re-expressing our flow rate of NH3 in stream 7. Now, just as we've expressed all of these components in terms of this new unknown X, we can also express our stream 5 over here in terms of 1 plus X. Okay, and that's simply notable if we divide throughout by N6 for this equation. And so in the same way, we have N5 of A being equal to N6 of A multiplied by 1 plus N7 over N6, and that is equal to N6 of A plus N6 of A times N7 over N6. Okay, and remember that this is equivalent to saying N7 of A over N7, so that's our mole fraction. Okay, so we're just re-expressing our mass balance in terms of X once again. And we perform the same expressions with all of our components. Okay, so ultimately we are expressing everything in stream 7 and stream 5 in terms of 3 unknowns. Okay, the unknowns are X, R, as well as N4, NH3. Okay, so now that we have expressed stream 7 in terms of our 3 unknowns, we've expressed stream 5 in terms of our 3 unknowns, stream 6 is expressed in terms of 2 unknowns. Now let's move on to our mixer and see what we can get out of that. Okay, so looking at our mixer, input is equal to output. So N2 of A is equal to N7 of A plus N1 of A. N1 of A is of course equal to 3, and this is my N7 of A, which we've solved at the top here. Okay, and we perform the following for all of our components. Okay, let's look at something a bit more complicated, such as the hydrogen. So my N2 of hydrogen is equal to N7 of hydrogen plus N1 of hydrogen, and that's already known, and we've proved this previously up here. Okay, so that's our mixer, and ultimately our stream 2 being specified in terms of our 3 unknowns. And one more interesting fact is that we can express our total flow N2 by adding up all of our component flows, and we obtain the following. Now we also know that the CH4 composition is 18%. So we can write out our CH4 composition as follows, right? 18% of N2, and that's equal to 12x plus 12, as we've seen before in the previous slide. There it is over here. So let's try and solve this, and ultimately if we solve, we end up getting an expression relating X to R and N4 NH3. Okay, so we are establishing that X is actually dependent on R and N4 NH3. So we now have one relationship between the 3 unknowns. Now it would be nice if we can obtain a relationship for our R and as well as our N4 NH3. If we can obtain that, then we can ultimately solve all of these three unknowns. And since everything else is expressed in terms of these unknowns, so let's move on and pursue the strategy of trying to relate our three unknowns. Okay, so we've completed our overall balance, our splitter, as well as our mixer. Now let's look at our separator balance. Okay, since we know what stream 2 is, we can easily get our stream 3 using the separator balance. Okay, and here are my balances. N3 of A coming in is equal to N5 of A plus N4. Okay, so there's nothing coming out at N4, right? No A coming out, so it's simply equal to N5 of A. And that's found as follows. Okay, and the same with CH4, N2 and H2. However, there is a split in our ammonia, our NH3. Okay, there is a split in our NH3, so we have N4 equal to 0.75 of N3NH3. And here it is as follows. We have our input, and that's equal to our output. So this is N4NH3 and N5 of NH3. And now applying our subsidiary relation of N4NH3 being equal to 0.75 of N3NH3, we obtain the following relationship. Okay, and this relationship relates N4 of NH3 to R and X. Okay, so we've already established one relationship here, and we can name that equation 1. And now we've established another relationship, equation 2. Okay, so we are nearing the end. Once we get one more equation, then we can solve simultaneously for X, R, and N4NH3. So we need a third equation. But now we've already expressed all of our streams. The final subsidiary relation that we didn't make use of as yet is the conversion. Okay, so we have been given 65% conversion, and that's equal to N2 of nitrogen minus N3 of nitrogen divided by N2 of nitrogen. And expressing all of these values in terms of X, R, and N4NH3, we get the following. Okay, and there's, as you can notice, there is no N4 of NH3 in this particular equation. So we end up getting a relationship between R and X. Okay, and that is our third equation. So now we have 3 equations and 3 unknowns. We can of course try to solve them. In equations 1 and 2, we can re-express R in terms of X by using equation 3. Okay, so simple substitution. We use 3 to eliminate R, and thereafter we can use equation 2 to express N4NH3 in terms of X. And finally, we can substitute all of this into equation 1. And this is the equation that we need to solve, and we can see that it's only in terms of X. So once we can find X, we can find R by this equation, and we can find N4NH3. Now if we manipulate this equation using some simple mathematics, we find that this equation reduces to a quadratic. And now all remains is that we can just solve for x. Remember that we get one value of x that's not sensible because it's negative. So we take the positive value. Okay, so this is just using our quadratic formula which you've known from high school. And so solving, and we get our x, and from there we can get r and N4NH3. And now once we have these values, we can express all of our streams. We can find all of our streams once our three unknowns are found. Okay, because we've already expressed it in terms of these unknowns. So that is how you solve the problem. And in this case, this problem required an implicit solution. Okay, where we carried our variables and we found relations for them and ultimately solved for all of our unknowns, for our three unknowns. It required an implicit solution. We just ended up with a simple quadratic. We didn't have to guess anything and use trial and error in any way. So it was a simple and implicit result. Okay, and that's the problem solved. Now we seem to have gotten lucky that we ended up with a quadratic to solve for x. However, what if in our mathematical manipulations, or what if we get a process where we ultimately end up with a cubic equation or something higher than a cubic equation? Then what? We can't simply use any quadratic formula or any simple equivalent formula to solve for very high order equations. And it is ultimately this fact that separates an implicit solution from an iterative solution. Okay, so for anything higher than a quadratic or even higher than a cubic equation, we will ultimately need an iterative solution. Now, what do I mean by this? In the case of an iterative solution, we would require an initial guess for our x value. Okay, and it needs to be an intelligent guess. We can't guess for negative x values or any other value for that matter. And we ultimately need to use more sophisticated root finding techniques. And there are three popular techniques. One is successive substitution, one is the Vex Tine Method, and the other is the Newton-Raphson method or the secant method. Okay, now let's consider our previous example where we ended up with our quadratic. Now, if we manipulated this equation differently, we could have actually ended up with a cubic equation. Now, a cubic equation is more complex to actually solve. However, we can use Newton's method to actually solve this cubic equation. And what's the procedure for using Newton's method? For one, we choose an intelligent guess. We know that x can't be negative. And we also know that the flow N7 is large enough to increase the composition of our methane from 1.2% to 18%. So x should at least be greater than 1. Okay, remember x is N7 over N6. Now, so the solution will be to keep choosing a large guess until we end up with a sensible result to solving that cubic equation. So let's look at Newton's method, and this is the formula for Newton's method. For our initial guess, x naught, we need to find f of x naught. Okay, so whatever we chose to guess, we need to find f of x. And we also need to find the derivative of f of x. Okay, and once we found these three values, we can compute x1. And what remains is to compare x1 to x0. And if it meets a certain tolerance, or if x1 is exactly equal to x0, then we know that we have found the actual root. We found the x value. However, if x1 is not equal to x0, then we let the new x0 be equal to our x1, and then repeat our Newton-Raphson formula. Okay, now depending on your guess, we could have, remember we are dealing with a cubic equation, which means that we could have up to 3 possible roots. So which root is the correct root? That might depend on our guess. Okay, so we need to make sense of what kind of root we have found. If we've ended up finding a negative root, then we'll know it's a wrong root, because we can't have a negative ratio for our flow rates. And if we do find a negative root, it means that our initial guess was actually wrong. So we need to choose a guess that is significantly different. Okay, and thereafter we repeat the calculation. Okay, so let's look at some guesses. Note that if we guessed x0 to be 10, and we go through our Newton-Raphson method, we'll end up with a root of -1. If we guessed an x0 of 20, we'll end up with a root of -1.2. Now both of these roots are not sensible. However, if we guessed a root higher than that, x0 being 25, we get a root of 34.14, and that is sensible. Okay, so this is obviously a sensible root. Now we may also use another method in addition to, well, as an alternative to Newton's method, and that is the Vex Tine method. This is a bit more complicated, so I wouldn't recommend it. But here are the steps. We simply rearrange our function f of x. Okay, so this is our f of x. And we can rearrange it until we have it in terms of only x. So we have x is equal to g of x. And now we need to find an initial guess for x and have a tolerance value. And we also need to set different limits and bounds, alpha and beta. Okay, and this is just going through the actual procedure where we can find our slope, gx of k minus gx of k minus 1, in other words our previous guess, over xk minus xk minus 1, xk of k minus 1. And thereafter we need to find this theta value, where theta is 1 over 1 minus the slope. And if theta is greater than alpha, then we let theta be equal to alpha. If theta is less than negative beta, then we let theta be equal to negative beta. And ultimately we can find x of k plus 1 by the following formula. And if x of k plus 1 is very nearly equal to x of k, if it's maintaining a certain tolerance, then we know we've found the correct root. So if we look at our previous example, we had f of x being this function here. F prime x would be simply the derivative of f of x, and we substitute that into Newton's method, or we could rearrange it in the form of x is equal to g of x. Okay, so we simply take all of this onto the other side and get g of x. and we use that for our Vex Tine method. And as you can see, we do end up with the same result. We have 34 point something, 34.14, 34.9. It fluctuates a bit. Okay, that's the nature of the Vex Tine method. And this is the Newton's method, where we have a more definitive convergence and also using fewer steps. Okay, and this is why I would highly recommend you use the Newton's method. Now, we can also use computer software. We don't have to actually follow through this entire method anymore. We can simply solve in Excel using different convergence tools such as goal seek as well as solver, and those functions actually employ these types of methods in their computation. Okay, so it's already built in, so things are very easy for you right now. You don't have to actually remember how to do this function. You can simply use it in Microsoft Excel and perform all of your computations there. And this is ultimately the way you will go about doing it in the workplace. Okay, so that's the problem solved.